Welcome to SCS Engineers series of mini webinars focused on carbon sequestration and deep well injection. In this series, we'll address the benefit of using computational models to develop critical pressure calculations. Today, Dr. Charles Hostetler will present the importance of this approach to identify a specific area influenced by injection of carbon dioxide, focusing on several points. One, understanding critical pressure early in your project is key to the project's success. Two, pressure buildup can complicate your relationship with neighboring landowners and maybe even limit your rate of injection. And three, the timing of when pressure fall-off occurs after injection is key to right-sizing your project. By modeling the system, this pressure fall-off timing can be incorporated into your critical pressure calculations. Charles has a wealth of knowledge and experience in permitting, regulation, and subsurface modeling. He hails from Central Illinois with a bachelor's in geosciences and a PhD focused in geochemistry. Charles complements our team with his expertise in delineation of areas of review and optimizing pore space utilization. Charles, take it away.
Thank you for that introduction, Stephanie. I appreciate it, and it's a pleasure to be talking with all of you today, and I appreciate your time and interest in the topic. On the cover slide, what I'm showing here is a hypothetical 200 million metric ton injection. It was never permitted or implemented. It was an office study. But the white outline is the state of Illinois. And what I want to do is introduce the group to the idea that we all want to sequester as much carbon dioxide as efficiently as we can in the subsurface, because that drives the finances for our projects. But we need to be mindful that large injection rates in certain geologic media can cause pressure buildup over a regional scale. We're going to look at the whole purpose of the Class 6 permitting program is to prevent endangerment of underground sources of drinking water. So there's injection of carbon dioxide and buildup of a plume, which is contained by the cap rock. And then pressure can cause migration from improperly abandoned wells and push brine up from the injection zone up into an underground source of drinking water. The CO2 itself, the supercritical CO2, is buoyant. It's less dense than the brine. And if there's any penetrations in the cap rock in the CO2 footprint plume, the CO2 can migrate up into underground sources of drinking water. So the whole purpose of the permitting program is to prevent this from happening and prevent your project from impacting underground sources of drinking water. On the next slide, we can look at pressure buildup in a project. So this again is a hypothetical. I think this was a 20 million metric ton project that was not permitted, but it was calculated a model buildup over a 50-year period. And you can see that initially there's a number of individual injection wells, and as injection proceeds, the pressure buildup from those injection points merges and forms an overall regional scale plume. Even for moderate sized projects, 20 million metric tons to 50 million metric tons in reasonably permeable injection zones, the area inside this pressure front can be surprisingly large. On the next slide, we'll look and see what the area of review is. So each project will have an area of review. It'll be driven by a combination of two things. One is the carbon dioxide plume itself, the footprint of the supercritical, that's shown in yellow and orange here. And then the second is where pressure can build up to an extent such that fluids from the injection zone could be pushed up into the subsurface. And that's shown in the larger blue area. Typically, the pressure front is bigger than the footprint of the supercritical carbon dioxide. You have to delineate this area of review, and you have to investigate any artificial penetrations in the area of review that could endanger underground aquifers. On the next slide, we'll look at critical pressure. Here's the injection well and the plume building up, and that's the supercritical plume footprint. And then you can see outside of that footprint, there is an abandoned well, and it penetrates the caprock, and the pressure that's induced from the CO2 injection could push brine from the injection zone up into an underground source of drinking water. The brine might have salt in it, sodium chloride. It might also have naturally occurring metals. And either one of these things could cause a threat to human health or safety. So that needs to be evaluated. This shows the potential 2 easy ways to evaluate it. It's based on superposition of states. So what we're looking at is a first state where a slug of brine is down at the injection depth. And you can see my colleague's Casey Garber's cursor showing you that first state where the slug of brine is deep in the injection zone. And then the second state is when the slug of brine has migrated up to the underground source of drinking water. And that's where that slug is up there. And what we do is we subtract the potential energy of the second state from the first state, and that gives us the pressure front. So there's no concept of time in this. That could take a day, a year, 10 years, 100 years. It's a simple subtraction of one state from the other. And it's very easy to do, and it's pretty unambiguous, and you can do it in an Excel spreadsheet. The problem is that it doesn't take into account time, and it's a very conservative estimate. In certain geologic conditions, it can give you a very low critical pressure front, and hence a very big area of review. On the next slide, a different approach, an alternate method is illustrated. This is construction of a numerical model, which is allowed by the EPA Class 6 underground injection control guidance. And it has cells built into it that discretize the underground source of drinking water up at the top, and a group of cells that represent the improperly abandoned borehole, and a cell at the very bottom that represents the injection zone. And what we're going to do is we're going to apply pressure at the very bottom, and we're going to see what migrates up through that improperly abandoned borehole into the USDW as a function of time. That function of time is very critical to understanding this. And the reason is shown on the next slide. This is a graph showing time. In this case, it's a pressure fall-off test, and the time is in hours. And the pressure is on the y-axis. And it shows you that for this pressure fall-off test, after you take the pressure off the system, the pressure front dissipates fairly rapidly. Not only does this happen in a short-term pressure fall-off test, but our modeling results show in typical scenarios such as the Illinois Basin, in Louisiana Permian basins, and in geologic sequences in California, that this, if you inject for 20 years and then stop injecting, by about year 25, 5 years into the post-injection site care period, the pressure front has pretty much dissipated. So we can take advantage of this in our modeling by applying pressure for a 30-year period, which is much longer than would be in real life, and figuring out whether or not the underground source of drinking water would become endangered. And then we can reason that if it doesn't become endangered under that 30 years of continuous overpressure, then in the real world, it wouldn't become endangered during the buildup of pressure, the achievement of peak pressure, and the pressure dissipation after the 20-year period. Okay. Casey is now going to switch to a model of this system. It's going to illustrate in a little bit more detail what we're talking about. This is a Petrosim and Tough 2 model of the subsurface. And we're looking at the underground source of drinking water from above. So we are in an airplane peering into the subsurface. This is a single phase 2-component model. It consists of brine and dissolved salt. There's no carbon dioxide in this model. The variables are pressure, temperature, and the percent of sodium chloride dissolved in the brine. Casey's going to rotate it around so you can see what it looks like. It's a rectangular model, and it's 1,000 meters a kilometer long and 2,000 meters thick. You need to make this model big so that the edges don't interfere with the pressure buildup where the center borehole is. And the bottom of it is about 750 meters below the underground source of drinking water. And so a number of these cells are inactive. We had to build them in just because of the way that Tough 2 works. Casey's going to turn them off and show you the cells that are active in the model, where mass and temperature and pressure can actually flow. So this is the active part of the model. The top of it is an underground source of drinking water that we're going to look at and see whether or not it becomes endangered. There's a big, long soda straw borehole that represents an improperly plugged well with a permeability of about 10 to the minus 10th meters squared, which is about 100 Darcy's. So it's very, very permeable. And at the very bottom of it, you can see colored in orange, is a cell that is in the injection zone that has brine from the injection zone, and it has pressure applied to it. So what do the initial conditions look like? We will look at the temperature first. And this is a geothermal gradient, and the underground source of drinking water is fixed at about 48 degrees C, and we can get that from site characterization data. And the base of the injection zone temperature is fixed at 68 degrees C, and we got that from site characterization data from our borehole, our stratigraphic test well. And then we ran this model to precondition it so that there's a gradient set up, a geothermal gradient set up for the initial condition. For the pressure, the initial condition looks like 10.9 megapascals in the USDW. And at the bottom, it's about 18.8 megapascals under natural conditions. We added an overpressure of exactly 1 megapascal to that very bottom cell. And that represents the pressurization pressure buildup due to injection. So what we're doing is we're testing to see whether a 30-year period of 1 megapascal overpressurization can induce brine flow from the injection zone up into the USDW. And then there's a salinity gradient as well. And so the USDW has about 6,800 ppm TDS. It's fresh water, relatively fresh. It's the lowermost USDW. And the injection zone itself is 12,500 TDS. And so, again, we preconditioned the model to have a salinity gradient in it. So what we're going to do is let the model run. This is a fairly simple model. It takes about half an hour to run. Tough 2, and we're going to look at the results, and we're going to see whether or not the aquifer is endangered. We're going to look at the pressure first, and you can see in the box where Casey's cursor is now, those are time steps, and what she's going to do is march through time steps. The first number of them are going to be a year apart, so this whole simulation is going to run for 30 years, and after we get to a certain point, we sped it up so that the time steps are 5 years apart. And what you're looking at is very subtle changes in the coloration of the cells as the pressure builds up in the pipe. And you can see just slight changes in the color scale. So what this tells us is that the overpressure at the bottom propagates slowly up in the improperly abandoned well. And now we're at the end of time. There's no overpressurization in the USDW itself, which is a good thing. It's important to notice that we used a big area for the USDW, and the boundary conditions are far away from where that pipe enters. And so the boundary conditions don't impact the accuracy of the solution, and the pressure front does not build up into the USDW itself. There's nothing really interesting to look at in the temperature because of the high heat capacity of the rock that all this passes through and the relatively small amount of fluid that's passing. So there's not really a big change in the temperature. We'll switch to salinity next, and we'll look at the change in the salinity. And this is the initial condition. And now brine is being forced slowly up in the pipe as she steps through. And you can see very subtle changes. And about this time, if you zoom into the top, you can see that a very, very slight salinity change has intruded into the USDW. And what time are we now, Casey? We're about 20 years into it. And at the end of this simulation, what we can do then is we can interrogate the data set, and we can determine the salinity of all of the cells in the USDW, and we can ask, what is the change in salinity of the USDW for this 30 years of overpressure? And if it's small, negligible compared to the mass of the aquifer itself and compared to drinking water standards and so on, then we can conclude that 30 years of overpressure does not endanger the aquifer, so that in real life, a buildup of pressure over 20 years to a peak and then a dissipation of 5 years would not endanger the aquifer. Right? So if we switch back, we'll come to the takeaways and the concluding slides. Compared to the simple potential energy-based approaches, the computational modeling approach that we're recommending in certain geologic conditions, it's more complicated and more time-consuming. It's not half an hour with an Excel spreadsheet according to a predefined equation. It requires additional documentation in your permit document. In permits we've written, this calculation is written up as an addendum to the AOR delineation, and it needs to be explained and reviewed. And it does require an operational definition of endangerment. So how much of that little salinity can you take, and how conservative does your calculation have to be? Is 30 years convincing? Those are all points that have to be discussed with the regulatory agency and resolved. On the other hand, the advantages that the computational modeling approach gives you is it's more mechanistic and conceptually understandable, I think, than a superposition of states. We're actually tracking the movement of parcels of brine over time, and we can make movies of it, and we can show what happens. You can use it to explicitly address uncertainty. Every 5 years in your process, you're going to be updating at a minimum every 5 years the area of review modeling, and you can update this critical pressure model as well as additional testing and monitoring data become available. And so in using the iterative approach, this fits into the overall permit feeding into AOR updates, then new additional testing and monitoring, and this approach is compatible with the overall permitting approach. And it provides a more authentic representation of the critical pressure and hence the area of review. Without this approach, you could convince yourself, if you don't think about it too carefully, that your area of review might involve 50 or 60 or 100 square miles. And with this approach, you can get a much more representative and authentic depiction of what the actual area of influence of pore space is. With that, I'd like to turn it back to Stephanie for the closing. Thank you for your time and attention.
Thanks, Charles and Casey, for the discussion and that demonstration of determining critical pressure. Charles and others on teams have presented numerous topics in SCS's mini webinar series. I invite you to check out the pre-recorded series and to stay tuned for more upcoming topics that we're currently developing to address carbon sequestration and deep well injection. In the meantime, please feel free to reach out to Charles, Casey, or me for more information, or scan the QR code on this slide below. On behalf of the entire SCS carbon sequestration and deep well injection team, we thank you for tuning in today.